Okay, let's get started. My only announcement today is that your Chapter 5 Achieve homework is due Monday. Again, this is a bit longer of an assignment, so I recommend that you all get started early. And that's it for announcements. We'll finish Chapter 5 today, so this weekend, take a look, or just keep an eye out for an announcement. I'll let you all know when I post the Chapter 6 PowerPoint, so you can have that ready for Monday. At the end of class on Wednesday, we were talking about concentrations, and if we're diluting a solution, we can use M1V1 equals M2V2, where M1V1 is our original solution, and then M2 is the molarity of our diluted solution, and V2 is the volume of that diluted solution. So this question, we're not going to make it an iClicker today, so you can ignore that. But it's another dilution question. So we are calculating the final concentration of sodium chloride after we take 1.25 liters of a 0.5 molar solution and dilute it to a total volume of 2.5 liters. So our initial solution that we are going to dilute has 1.25 liters, so this is V1. Its molarity is 0.5. This is M1. And our final volume after diluting, we're adding more solvent, which is water, is 2.50 liters, so that is V2. We're looking for the final concentration, so we're looking for M2. Since we are doing a dilution question, we can use M1V1 equals M2V2. You could plug everything in here and then solve for M2, or at this point we can rearrange the equation where M2 is equal to M1V1 divided by V2. And we have all of the values on the right side of that equation, so we just plug them in. M1 is original molarity, 0.500 molar. V1 is the volume of that solution that's getting diluted, 1.25 liters. And then V2 is our final volume, 2.50 liters. Solving for M2, our final concentration is 0.250 molar. When we've completed a question like this, we can think, does this make sense? Does this molarity make sense? We're taking a molarity of 0.5, we're diluting it, so our final molarity should be lower. We're going to have a lower concentration, and that is correct here. So if you're ever doing a dilution question, looking for the diluted molarity, and you end up with a molarity that's higher than your original molarity, then something went wrong along the way, and you know you should go back and check your work. So this question and the questions that we did with dilutions on Wednesday are all scenarios where we take one solution that has solute and then only the pure solvent. So another amount of some volume of solvent that has no solute in it, and we're mixing them together. So the number of moles of the solute stays the same, just the volume changes. But there may also be other scenarios where we have two solutions with different concentrations and we mix them together. So both solutions have some solute present and some solvent, we mix those together, we can calculate that final concentration given those solutions as well. When you are mixing two solutions that have both solute and solvent present, the total number of moles in your individual solutions of solute will be the same number. If you add those together, that will be the number of moles of that solute in your mixed solution as well. And then we can also add up the volumes, and that will be the total volume. So that's our process of calculating final molarity. We need to know individual moles of solute total, and then total volume. That's what this slide shows. To find the moles of a solute in a solution, we need to know the volume of that solution that's getting added. We multiply by molarity, and we can get the moles of the solute. We do that for both solutions and add them together. That gives us total moles of solute. We add volumes together, and that gives us total moles, or total liters of solution. So let's do an example here. We have two solutions, a 1.25 liter solution of 2.25 molar sodium chloride. And then another solution, we're adding 3.5 liters of that solution, and its concentration is 2.45 molar. So two different molarities, different amounts of solution, we're adding them together. Here's our information. I'll just put M for molarity there. We'll say this is solution 1. And then this will be solution 2. So to find the final concentration, we need total number of moles, so of solute. Find moles of solute from solution 1, moles of solute from solution 2, and add them together, and then total volume. So let's do solution 1. We're looking for moles of solute. We can find that by taking our volume. We have 1.25 liters, and multiplying by concentration, 2.25 moles per liter. So that means for solution 1, that contains 2.81 moles of NaCl. Do the same process for solution 2. We're taking 3.50 liters of the solution, which has a molarity 2.45 moles of NaCl per liter. So when we mix the specified amounts of each solution together, in our final solution, we have 2.81 plus 8.58 moles of sodium chloride, moles of the solute. So that will give us total moles of solute, and to get our total volume, we just add the two volumes together. So our molarity of the final solution total moles of our solute, sodium chloride, divided by total volume in liters. So that's 2.81 plus 8.58 moles. And then our total volume is 1.25 plus 3.50 liters. That gives us a final molarity of 2.40. So note that we cannot add the molarities together. We can't add molarities directly together because we're taking a different volume of each amount and adding those together. To get the final concentration, you need to know total moles of solute over total volume. And note that we cannot use M1V1 equals M2V2 because we're not simply doing a dilution, we're adding another solution with its own concentration. So M1V1 equals M2V2 only for dilution. Any other question, there's a different process. Okay, questions on this question or this problem? Okay. Next section's similar concepts, a little bit more detail though. But before we move to that section, in this example, we have solutions of sodium chloride. Do y'all remember what happens if we take a solid sample of sodium chloride and add it to water? What does the sodium chloride do? It creates ions. It dissociates. So sodium and chlorine dissociate into their ions. So if we have sodium chloride in solution, we don't have if it's dissolved in water, we don't have solid sodium chloride, we have sodium ions and chlorine ions. And so we can describe the molarity of specific ions in solution if we have a compound that dissociates into ions. So this next section is about molarities of ions. And just a reminder, you all have seen this image before, but this is a particle image of what sodium chloride looks like in solution. Sodium and chlorine are not bonded to each other. They dissociate into ions. We see sodium cation surrounded by water molecules, and chloride anions surrounded by water molecules as well. So if we're describing the molarity of sodium chloride, really what we're describing is the molarity of these individual ions. Now, in sodium chloride, these ions dissociate in a 1-to-1 ratio. For one sodium chloride solid mole of solid sodium chloride, we have 1 mole of sodium cations and 1 mole of chloride anions. But that's not always the case. We've seen different ionic compounds. So here's an example with nickel chloride. So if we have nickel chloride, 1 mole of solid nickel chloride added to solution, that dissociates into 1 mole of nickel 2+ and 2 moles of chloride ions. We have 2 chlorine atoms or ions here because we have a 2 subscript in that formula. So for every 1 mole of nickel chloride, we have 2 moles of chlorine atoms or ions. And so if we know the concentration of the compound, we know how much sodium or nickel chloride is added to solution, and we can use this like a balanced chemical equation and determine the concentration of individual ions. But this equation is necessary in order to do those calculations. We need to know for any ionic compound how many of each ion is going to be present in solution. So 1 mole of nickel chloride creates 3 total moles of ions when it's dissolved in water. And so with that, I have an iClicker question for you. This one's not in your slide, or in your slides. Oops. Okay. So we have barium chlorate. We're adding that to water. We have 1 mole of barium chlorate. The question is how many total moles of ions are present in that solution? And if you're not sure where to start, you should write out the ionic equation for the dissolution of barium chlorate, or dissociation of barium chlorate. Is there one more minute here? Six. Okay, I think we've got, oh, I sorely miscounted. Alrighty. Ending here, let's see what we're thinking. Same distribution as in our earlier section. Okay, so when we have barium chlorate present in solution, we need to think back of what ions are present here. Well, barium's in the second column of the periodic table, so barium as an ion has a +2 charge when it's dissolved in solution. And then our chlorate anion is a polyatomic ion, so the ClO3 stays together. That has a -1 charge. But we see from the original compound formula, we have 2 chlorate polyatomic ions for every 1 barium. So that means we have, for every 1 mole of barium chlorate, we get 1 mole of barium and 2 moles of the chlorate anions. So total in solution, we have 3 moles of ions. Okay. So next question, we are finding the molarities. We'll do this one together. We're finding the molarities of ionic species, so of the ions present in a 250 milliliter sample of an aqueous solution that contains 1.75 grams of ammonium sulfate. So we have an ionic compound, ammonium sulfate. A certain amount of that compound, it's given to us in grams, a certain volume, so we can calculate concentration But we want to know the concentrations of the individual ions, so we need to know what ions are created by ammonium sulfate. So we start with a neutral solid and we're trying to find ions, concentration of ions. We should write out that equation where we show the dissociation of ions. So we have ammonium sulfate. We add it to water and the ions dissociate into, or the compound dissociates into its ions. So looking at our compound, we have ammonium and we have sulfate. Ammonium is NH4 plus, that's on our list of polyatomic ions. In the formula of the solid, NH4 is in parentheses with a subscript of 2 after the parentheses. So that means there are 2 moles of NH4 plus ions for every 1 mole of ammonium sulfate. And then we have our sulfate anion. Again, that's on our list of polyatomic ions. And we have just 1 sulfate ion for every ammonium sulfate compound. Now remember, concentration in general or lowercase c, we calculate concentration. We've done specifically molarity, but there are other units of concentration. But even molarity, this is generally the amount of solute over the volume of solution. So using the information provided, we need to calculate the amount. We're looking for the molarities of ions. So the moles of each ions divided by the total volume of solution. So we're doing the same calculations. Either way that you do this, there's multiple ways to calculate the molarities of the ionic species. I'm going to verbally explain one, and then we'll do one on the slide. One way would be to first calculate the total molarity of the full compound, ammonium sulfate. So you convert grams of ammonium sulfate to moles of ammonium sulfate, convert milliliters to liters, you find the molarity of ammonium sulfate. So moles per liter. And then you can use the balanced chemical equation to say if our original molarity is 1 molar, then the molarity of NH4 plus is 2 times that, so that would be 2 molar. Molarity of sulfate is 1 times that, so 1 molar as well. So that would be finding molarity of the full compound first and then converting to molarities of ions. What we're going to do is one long math equation going from the the information that we're provided as far as amount of ammonium sulfate and volume, and then convert all the way to molarity of the ions. So just combining all the steps into one. So we'll do one ion at a time. Finding the molarity, we'll start with ammonium. So for NH4 plus, we're finding molarity, so we're starting with the amount of the solute divided by the volume of the solution. We are provided the amount of ammonium sulfate, and we'll end up converting that to moles of ammonium. And then we're provided 250 milliliters, and we'll convert that to liters. So starting with amount of solute, 1.75 grams of the full compound, divided by volume, 250 milliliters. we'll start by converting grams to moles and then get to moles of ammonium. You could start by converting milliliters to liters and then worry about moles, that's fine. But we'll do grams to moles first. So we have grams of ammonium sulfate. We need to convert to moles of ammonium sulfate. Molar mass is 132.14. So we've got moles of ammonium sulfate, but we want to know moles of ammonium. Now we use our balanced chemical equation. For every 1 mole of ammonium sulfate, that dissociates into 2 moles of ammonium. So we have 2 moles ammonium, NH4 plus, over 1 mole of ammonium sulfate. This is why it's important to include all of your units, specifically what mole in grams you're talking about, which compound or which atom, so that you can kind of keep track of everything as you go along. So we've converted to moles of ammonium. That's the numerator for molarity. We just need now to convert milliliters to liters. Ten to the third milliliters for 1 liter. And so our final value is 0.106 moles NH4 plus per 1 liter solution. So that means the molarity is 0.106 molar NH4. So that gives us molarity of ammonium. We go through the same process to calculate molarity of sulfate. So starting with the information given, amount over volume, 1.75 grams ammonium sulfate over 250 milliliters. We convert grams to moles using the same molar mass of ammonium sulfate. So we're at moles of ammonium sulfate, but we want molarity of just the sulfate anion, so we convert using the balanced chemical equation. For every 1 mole of ammonium sulfate, that dissociates into 1 mole of sulfate, SO4 2-. So we've got moles of sulfate. Now we just have our last step, converting milliliters to liters, 10 to the third milliliters for every 1 liter. We put milliliters in the numerator because we need to cancel out milliliters in the denominator over here. And we want moles per liter, so we want liters in that denominator at the end. So this is 0.0530 moles of sulfate per 1 liter. So molarity of 0.0530. So again, we can look at our two answers and see, do these make sense? This is, the two molarities are different. One's lower than the other. Does this make sense given our equation, our valence chemical equation? Well, given any amount of NH4 to SO4 ammonium sulfate, we produce 2 moles of ammonium and 1 mole of sulfate. So our concentration of ammonium should be higher than our concentration of sulfate. And that's what we see here. Our concentration of ammonium is 2 times the concentration of sulfate. Questions on this? Okay, well, our next slide, let me know if you have questions on this as well. This will be an iClicker, so I'll start that in a second. We have another scenario where we're starting with a solution of a ionic solid that dissociates into ions. You already have the concentration of that solution of the whole compound. And so your task is to find the molarity of the individual ions. So your first step should be writing out this balanced equation that we did at the top here. And then starting with the molarity provided, what's the molarity of the individual ions? I know some of you are still writing, so I'll keep that slide up and I'll start this quiz for you all. And then questions about this slide or the iClicker? Good time to ask.
I mean, guys, actually, wait, I don't think it's that comfortable.
Oh, the total solution. Yeah, like, well, the first, you mean specifically in this one? Yeah, so that you start with that and you're gonna subtract it, and then conversion, we're gonna end up with. have how divided by milliliters. And then you can
Are we supposed to find the molarity when we have that?
okay. So molarity goes for 6.1 if it's 0.04 molarity.
Oh, yeah, okay.
So you have to make this would be 0.04. It's yeah. So you'll start with molar and 0.04 moles of aluminum Okay. So you have 4 moles of the and we say that would be your first finding group. We'll try 1 more minute here. So when the time is 7:40.
I know.
So here you just want to Okay, we're gonna end it here. All right. In this question, we have aluminum chloride, AlCl3. We're adding this to water. This separates into its ions Al3 plus and then Cl minus. In our formula, since it's AlCl3, we're getting 3 Cl minus ions. So chlorine has a coefficient of 3. We all quiet down, please. Thanks. So we have 3 chloride ions because of that original formula, AlCl3, 3 chlorines. So if we have 0.04 molar solution, that means we have 0.04 moles of aluminum chloride. That's what the information we're provided right here. 0.04 moles of aluminum chloride per liter. Then we use our balanced chemical equation to go from moles of aluminum chloride to moles of aluminum. So for every 1 mole of aluminum chloride, we have 1 mole of aluminum 3 plus ions. So the molarity of aluminum 3 plus is 0.0400 moles aluminum per liter, or 0.0400 molarity, capital M. For chloride ions, we have, again, starting concentration, 0.0400 moles of aluminum chloride times 3 moles of chloride ions because of that coefficient in the chemical equation for every 1 mole of aluminum chloride. So our concentration of chloride ions is 0.1200 moles per liter. Yes. Thank you. Okay, we've got to move on. A little bit more to get through before we're done with chapter 5. So this section here, there's no question that we've covered basically all of this in our previous examples. The section in the book just shows this flow chart and then a few examples of how to do conversions if you're given volume of the starting material. Then you need molarity to get to moles. Or mass of the starting material, you need molar mass to get to moles. And then anytime you're going from moles of starting material to product or product of starting material, you need the balanced chemical equation to do that. So you can use this flowchart as you're working through problems. We've done most of this through our previous examples, so I don't think we need to do any more examples here. So our last section is about titration. So, excuse me, we're switching gears a little bit here, so let's get focused on titration. We all quiet down, please. Again, will you quiet down? Okay, so titration is a lab technique. We use this to determine the concentration of a solution where we don't know that concentration. So the types of titrations we'll talk about are titrations with strong acids and strong bases. We'll get to more complicated titrations next semester. So it's a lab technique to determine number of moles of a substance dissolved in an aqueous solution. One reactant, which we call the standard solution, has a precisely known concentration. So we have a standard solution with a known concentration. We have careful volumes measured of the standard solution and the sample. And then we use the mole ratios and volumes to calculate the sample concentration. So the sample with an unknown concentration, we can find its concentration through titration. Yes.
You said that the sample concentration is unknown.
So we have one sample with an unknown concentration and another sample with a known concentration. And I'll show you what that looks like on this next slide. So this is the lab setup for a titration. In the Erlenmeyer flask, down here is our sample with an unknown concentration, but we know exactly what the volume is that's present here. We have a burette stand that holds this burette. That's the name of this apparatus here. The burette holds our standard solution. In this example, we have an acid solution here and a base solution in our burette. We can carefully measure how much volume of the standard solution is added to the unknown solution. And we know the molarity, so we know the concentration of our standard solution. So this is our titrant, what's getting added. The titrant is added dropwise to our solution with unknown concentration. So that when we reach an equivalence point, which is when, let me back up. In our unknown solution, we also have an indicator. So the indicator will change color when we have strong acid down here. When we have reached our equivalence point, where the number of moles of acid is equal to the number of moles of base, that's when the indicator will change color. So we know that we've added enough base to react with all of the acid present in our unknown solution. So then we can take the volume of the base that's added to calculate moles of base that were added. That's the moles of base that were reacted with our acid. So that's the same number of acid molecules that originated in our solution with an unknown concentration. So the next slide goes through all of these steps. We have one reactant, which is the titrant, is slowly added to the other. Typically, the titrant is in the burette, and the other reactant is in an Erlenmeyer flask. The shape of the Erlenmeyer flask, it gets narrow at the top. That allows for swirling without as much risk of something splashing out. So that's why we use typically an Erlenmeyer flask. We add an indicator to the reaction to indicate the end point through color change. And so at the end point, which means we're at or very close to the equivalence point, this is when we reach the color, the indicator changes color. This means the substance being titrated has reacted with the titrant. So all of the substance being titrated has reacted with the titrant. So for a strong acid and strong base, these are the only types of titrations we'll talk about here. This is where the concentration of the acid is equal to the concentration of the base. And the volume of the titrant is determined by comparing the initial and final burette volumes. We're going to do this problem here. So I'm going to walk through it because we need to finish chapter 5. So I need 1 or 2 more minutes of you. So it's a titration question. A student prepares a solution of HCl. So we've got a strong acid in water. We want to know the concentration of that strong acid. We have a 25 milliliter portion of the HCl solution. So we know the volume of our solution with unknown concentration. We don't know the concentration. But it's titrated with a 2 molar sodium hydroxide solution. And of that 2 molar solution, we use 37.25 milliliters. And then we're looking for the molarity of HCl. Well, when we have HCl and NaOH react with each other, this is a strong acid, they're in water, so aqueous, and a strong base, they form water, so acid-base reaction, and then sodium chloride. So hydrochloric acid and sodium hydroxide react with each other in a 1-to-1 ratio. So if we know the total number of moles of sodium hydroxide added to solution to reach that equivalence point, that's when all of the moles of acid have reacted with the base. So that means if we know the number of moles of base, we know the number of moles of acid. So if we start with 37.25 milliliters of sodium hydroxide, this is the amount of titrant that's added. We need to convert milliliters to liters. And then convert volume to moles of sodium hydroxide using its concentration. So 2.000 moles NaOH for every 1 liter. So volume added, converting to liters, and then converting to moles of sodium hydroxide using its concentration. So now we've got moles of sodium hydroxide added. Well, for every 1 mole of sodium hydroxide, we've got 1 mole of HCl. So now we're using our balanced chemical equation to go from moles of NaOH to moles of HCl. And this gives us 0.07450 moles of HCl. So this is the number of moles of HCl present in our initial solution. Our initial solution with unknown concentration, we had 25 milliliters. So we have to calculate molarity of HCl, 0.07450 moles of HCl, divided by the volume of that solution, 25.00 milliliters, and then just converting milliliters to liters. This gives us a concentration of 2.980 molar HCl. So as long as you know the amount of titrant added, you've got that balanced chemical equation, you can find moles of the unknown acid solution, and then you've got the volume so you can calculate molarity. All right, keep an eye out for Chapter 6 PowerPoint this weekend. If you didn't pick up your Scantrons Wednesday, I've got them here. Hi. Okay. Okay, I'll take a look. Yeah.